Okay, morning, everyone. So my name's Scott Gourlay. As was said, I work in Pfizer in Sandwich. A little bit about myself. I joined Pfizer 5 years ago, and also I think it's probably worth mentioning, so I've had a few comments. Pfizer is still at Sandwich. Went through a big downsizing. It's actually increasing, I would say. It's not going back to the level it was, but there's probably about 800 to 1,000 Pfizer employees in Discovery Park and Pfizer now. Predominantly all R&D. The bit that I'm in is clinical supply. So we have a small pilot plant kind of facility there, twinned with a place in Connecticut, Groton, and that's where all the oral solid dose clinical supplies are made between those two sites. So that's where I work. Previous to that, I was at GSK for 25 years, and I thought I'd give a mention to Birmingham University since I'm back in Birmingham for first time for a long time, but I did a couple of degrees here quite a long time ago, but it's a good place to be, Birmingham. So what I'm going to talk about, I think the title was slightly wrong as well, so I kind of stepped into this at last minute. So the title of this is really around continuous manufacturing and how an accelerating portfolio and development through continuous manufacturing, and there's a bit of that I noticed in the last presentation, and GA as well, a big part of that. I think they've got a presentation this afternoon, so I hope I don't kind of cover the same points too many times. So essentially what we've thought about in terms of the technology, how we've implemented it at Pfizer, particularly within the R&D clinical supply space, the impact on the portfolio, and then some other pieces around control strategy, modeling, etc. So this is going back quite a while, actually, in terms of the very beginning, but I guess the kind of thought around continuous manufacturing was a chance to just not implement an advanced technology, but to think about the whole development cycle for us and what it would mean and how you could bring together science, manufacturing equipment advances, process control, PAT, bring that all together as one and try and kind of change the mindset of development and digitalize it a lot further. And so we've been going at this for, I think, 10 years. As I say, I've only been around for 5 years, and it's been a hard journey, I think. But you can see now the impact that it's having and where it's saving time, particularly around modeling, the digitalization, and bringing together some advances in manufacturing technology all together, as opposed to just putting technology on existing platforms. So that's just a kind of slide, sort of trying to pull all that together and say what we were trying to do at the beginning. This is a kind of, I guess, that one of the benefits that was seen from the beginning, and I'm sure people are fairly familiar with, sort of classical current state of development in terms of under 10 kilos, a batch and bin process, roller compacted processes are a kind of typical process that we would do in Pfizer, and you would scale up. But you'd scale up at each stage, and there's time taken there between phase 2, phase 3, and then into commercial. The bit that we've been working on, or particularly my team and Sandwich is working on, is really the bits around the clinical development, so phase 2, phase 3. We have got some commercial capabilities, but as yet that's still lagging, I would say, a little bit in terms of the commercial capabilities. So instead of that classical route is use continuous tablet manufacturing. That's kind of set up there, and you cut out those tech transfer processes, or you reduce them greatly. You can use the same machine, just running it longer from an hour to several hours to increase your batch size. Fairly flexible. You can, if you really want to, you can run 24/7. So you can get any kind of output you want from it. This is the rig that we have in Sandwich, or the start of it. So what was there to begin with? There was kind of some of its existing technology. So the tablet press, for example, is a standard tablet press. How that works and the understanding of that is kind of already there. Material transfer systems, nothing particularly funky or new in that. Gravimetric feeders used. So there was a lot of existing stuff, but as I say, it's kind of bringing it together. And then what's new in this technology? For us, we went for vertical powder mixing. There's the integration of the NIR into the tablet press for control. You've got real-time control and diversion of good product, bad product coming from that. Computational modeling. At the beginning of the Pfizer kind of project also, we were looking very much at a pod-based facility, and one of our units is in a pod, so kind of like a shipping container. You can pre-build it in there, and you could move it around. So yeah, as I say, the first unit was done like that. Actually, the subsequent units have been put into more traditional kind of fixed-place buildings, but it did work in the pod. Pod-based sort of facility. We just haven't progressed that. This is a picture of our actual unit in Freiburg in Germany. There's a continuous coater there at this end. You've got the powder handling system through the window behind the steps at the back. On this setup, we've actually got a wet granulation unit as well, which is that middle piece. But that's actually a picture of the manufacturing area in Freiburg, Germany, where they're doing both development and commercial manufacturing through that. As I've said, yeah, raw materials, bin transfer, vacuum transfer up to the top rig there. Continuous blender sits above the tablet press. You can't see that brilliantly well there. I've got plenty of other diagrams, and I've actually got a video of this run of how it runs in the presentation, and a standard Courtois tablet press. As I said, we have now started to look at wet granulation as well. So similar powder handling. The tableting's the same, just the middle bit in terms of the wet granulation and the fluid bed dryer in there. And we added film coating fairly recently. So I've got a kind of sequence coming up of what we did. This may be worth, if this is going to work, just gives, it's a few minutes, and it's no sound, but it'll give you an idea of the machine, how it's running. So 6 compact feeders sitting above your tablet press. The pneumatic conveying of the material in. So I guess one of the key things there is that the stabilization time is pretty short, so you get a good constant feed rate. The kind of heart of it is the continuous mixing technology. So you've got upper and lower. Our units are designed for 5 to 30 kilo throughput. We are looking to increase the throughput. We're also looking at some different impeller designs, which we feel are going to give some better mixing at the moment. Key at the bottom there is the exit valve, or the gate valve at the bottom, allows good control of your hold-up mass. One of the other points around our kind of unique points around our machine is the sequence and the control of charging. So we charge the hoppers and get it initially and get a steady state before we start the tablet press. So we charge the system and then go into automatic mode. I'm not sure if I'm not sure if we put these together or they came from GA. So apologies if they're combination. Yeah. So yeah, key part of the control is the NIR probe sitting there above the powder deck. And then this is just giving some examples here of what happens when you get pauses, stoppages, and the system stops, and diversion of product is automatic into good and reject powder tablets. So I think that's probably see if I can forward this on a bit. Yeah, okay. I think that's probably gives a good idea. I don't know how I can talk to people if they want some more details in terms of how the unit run, but it gives a good idea. I think this one is just skipped onto this. It's got a little bit around the continuous coating, which is worth showing as well. Some of this is the same at the beginning. I think this is why my presentation didn't transfer as well. Way too big. Yeah, some of this is very similar, but I think we move on to a little bit around the coating. Yeah, so this is recent. Again, I got some sort of evolution in Pfizer, but we installed in the US in our Groton facility continuous coating probably 18 months ago. A lot of our portfolio has moved to being coated. So this is now up and running, and we're in the process of purchasing a second unit in Sandwich. Okay. So let's talk a little bit about that. So this is over, as I say, I think this is over around, say, a decade, 10 years. Going back, the first units were the continuous DC units put in Groton in Connecticut. That's the sister sort of site to mine, making clinical supplies in Groton. They then added the continuous film coating. That's the top line there, both in green. What are we working on at the moment? We're adding wet granulation and also adding a development scale into our development area, a continuous coating. And then in Sandwich, which is the bit that I'm involved in, leading a project there, we started 18 months ago-ish, and GA are building us a whole unit. So it doesn't include wet granulation, but direct compression and continuous coating. I think it's being delivered actually next week. So FAT was recently done, so we'll have capability there. We also have capability in Freiburg, Germany, which is a commercial manufacturing site for Pfizer. Unit in there and up and running. And they've also added continuous film coating, and they have a commercial unit which just does blending and dispensing. So what have we actually done with these units? So that's kind of some of that. What I've just talked about is really the history and the trajectory. Well, what have we actually done with them? So back in sort of 2015 was the first one. So actually it's less than a decade. You can see in the picture there, that's what I'm talking about in terms of pods. So the one that went to Groton went in these kind of shipping container pods, prefabricated. The idea there was there'd be portable, which is the acronym that I'm using, PCMM. So one of the bits of it was portable. They haven't been portable. That's fairly fixed, as you can see. But the theory is they can be portable. We started our first clinical batch on their product called Durismo. sort of halfway through 2016. The FDA included it into their emerging technologies group midway through 2017. We started another product, Cibinquo, around that time in 2017. The NDA for Durismo was submitted in 2018, and actually launch was done from that facility, which is really a clinical facility, but was qualified for both commercial and development. There's some sort of pictures. The picture in the middle there is the development unit at Sandwich, not the full unit. Doesn't have a coater. Just was put in as a part of development. Picture of Freiburg. That's the unit in Freiburg. So, yeah, launch in 2019 of Glastigib, as I said, came out of Groton commercially, then was transferred later. But that was the first commercial. So development done on the unit, the continuous unit, and commercially launched out of Groton on the continuous manufacturing rig. Cibinquo was also included by the FDA into their emerging technologies project. Continuous film coating a bit later on, 2019, prior to the pandemic. That's the unit gone into Groton. Launch in 2022 of Cibinquo, which is abrocitinib. So two products on the unit so far launched. And I guess the question is, in terms of the title of my portfolio, have we seen acceleration in the development space and the development time for those two products? The answer is yes, we have. I guess there can be some debate because every product is different, but if you take a kind of normal timeline from phase 3, we would be talking kind of 36 plus months of development time. And you can see, obviously, that scale up is what we're targeting, and perhaps the development and manufacture at the beginning. The idea or the kind of premise for the acceleration was, as I say, taking out that scale up time, reducing the development time in phase 3, and looking for kind of 9 months if you add up kind of phase 3 cut by 6 months, and you're filing as well. 3 months because of the scale up there. So kind of that was the target, looking for kind of 9 months acceleration. This is kind of what we found on the first few products. So the top one there is a kind of more traditional 2.5 to 3 years, actually quite fast, 22 months. RFT is kind of the end of phase 3 for us, or the sort of middle of phase 3. And then these two, Glastigib and aprocibin, are the two products I talked about there. So Glastigib saved sort of half a year, 6 months plus. And then if you look at abrocitinib, that was 14 months, so even more savings. I think that's the thing you need to think about as well, is that as you get used to this technology, and as I say, you build the computational models, get the regulators are fully involved in all this now, you kind of find more opportunities for saving. It's kind of enabling other things. So I think we can expect to continue to hit those accelerated times, and possibly find even more time out of the cycle, particularly around the even earlier than the RFT in phase 3, in phase 2. So that's real data that was presented back to Pfizer. So it has achieved what it was set out to achieve in terms of the faster development times. And I guess there's also, I think, well documented that there are other reasons for continuous manufacturing as well. So the quality, the sustainability benefits that you can get. Direct compression potentially allows higher drug loading than conventional roller compaction, so you can get higher drug loading, less excipients, so there can be cost savings there. Those things I think are, for us, I think that, those things are definitely still possible probably more work to be done on that side in terms of actually producing cost savings. And I think within Pfizer there's a constant debate about that one, particularly from commercial, is where are the cost savings? Because the investment is high. So where are the cost savings? But I think the first thing that we have clearly demonstrated is there is an acceleration in development times through scale up, and there is a quality improvement as well. And then just a couple of other things I was going to go through. So one of the unique things that Pfizer have gone through, and again I'm kind of relaying this as a sort of messenger because I wasn't there in the initial selection, is the vertical mixing. I think probably more people are more familiar with the horizontal mixing, but some of the key features of the vertical inline mixing that we think distinguish it and make it a good option are that the first thing in terms of your development and your control is that you can independently select the target set points there, and they're particularly having the ability to control the hold-up mass. We believe gives an advantage. It allows some dampening. You can increase your hold-up mass, some dampening of the kind of effect of any variation on the feeders, and you can. And also, I guess there's a kind of by having a vertical setup, you can charge up front and get a blend up front. So the residence time distribution. From our information, I've got some charts on this, is very good. It kind of approaches very quickly ideal mixing by having the vertical mixer. And as I said, you're kind of efficient at the beginning of your batch. You can prime and you can set up, and then you can transition fairly quickly into a continuous mode. So I think those are the three things that we feel are kind of key features of the vertical mixing and have some advantages. I've got some charts here really just showing, this again is showing, probably best to flick through it. Because you've got control of the various parameters, you can play around fairly easily with these targets, either to dampen some feeder variability by increasing, as I said, you can increase your hold-up mass target, and that's been controlled by the exit valve. You can increase your impeller speeds independently. So if you're having problems with tablet formation, you can try reducing them, getting some stronger tablets, or vice versa. So it allows for, I think, good control of those parameters independent of each other. There's more interlinking with the horizontal mixing of those parameters, so they interact and affect each other more. I've just got to sort of again nick these slides. So there's a number of journals published around modeling continuous mixing. I could share those. And a little bit more detail here, just in terms of the setup. This is what I was talking about in terms of approaching ideal mixing. So these are a number of experiments that were done in Sandwich on our development rig. You can see there the kind of speed there to get to an ideal mixing, and that's done at various throughputs. You can again maximum 30 kilos on our rig. They've been done at 30 and 15 different speeds with different hold-up masses. So high at 850 grams, fairly low down to 500, and a range of RPMs. And through all of those, you can see that you're basically approaching very quickly ideal mixing in a matter of seconds, minutes, short number of minutes. Again, just looking at the ratios and various different experiments we've done. Okay, just to talk a little bit, so the kind of next phase, or what's worked on a lot, and is the digital twin. So we have good modeling of our process. You get a huge amount of data. That's, again, difference with the continuous mixing platform. You're getting a massive amount of data all the time, so you're able to do much more modeling. You're able to live monitor the process and see what's happening compared to batch manufacturing. And we've created a kind of virtual PCMM DC process, which is, again, really saving us time in terms of setting up and putting new products on there. It's also allowed us fairly accurately to look at the envelope of products that will fit in. And one of the things that we're trying to do now is address and increase that envelope, because there are particularly some APIs that just won't suit going on the continuous manufacturing. And a lot of the work we're doing now is trying to increase that envelope. So wet granulation is part of that, I guess, increasing the envelope of products you can put on there. But we're also looking at some low-dose stuff as well. So yeah, lots of good work being done in terms of process modeling, lots of understanding that we're getting around our products and which products are suitable to go on the continuous manufacturing unit and which aren't. I don't think there's much to say. Yeah, I'm going to flick through those. And then I think this is my last slide, actually. Just mentioned this. So we from a commercial point of view, we're looking at increased throughput. So at the moment, in terms of the continuous mixing, it's a 6-inch diameter mixing chamber. We're looking to increase that to 8 inches to give probably at least, I think, up to probably 100 kilo throughput, possibly maybe a little bit less than that. We're continuing to do some computerized modeling. We've implemented wet gran in Groton. We're not doing that in Sandwich at the moment, but we are already going into our first kind of clinical batches with wet granulation in Groton very shortly, and Freiburg, and looking at very low doses again by altering feeder screws and things like that, trying to get some low dose work done. I've talked a little bit as well about impeller design. So there's a kind of a fair amount of work ongoing, and as I said, it kind of accelerates some of this. When you get this unit, you get into the computer modeling, it gets many more people in your business aligned and focused on this, and with all the data, you can see many more opportunities. Okay, so that was my last slide. With this giving you a quick run through of what's happening in Pfizer. Any questions?
All right, thank you, Scott. Any questions for Scott?
Yeah. Hi there, very interesting.
Hi.
I see you're both working in similar areas. One of the questions was, you started to look at it on the last slide where you sort of pointed to low dose. What are the limitations on the continuous blending? And you know, when you say low dose, what exactly, what sort of numbers are you looking at there in terms of low dose?
I think we're looking at kind of down, really, well, ideally down into the kind of sort of 0.2, 0.3 meg kind of dosage. Yeah, and I think mainly, well, there's some sort of, there's work to be done, but what we're looking at is kind of essentially changing the screws and the gearboxes of those feeder units and then checking the control. I think that's probably going to be possible. Again, it comes down to some of the way we control the unit with a hold up mass, so we can play around with that and make sure we get good blending by playing around with the hold up mass.
So I saw you mention about digital twins, and you mentioned some of the parameters, CPMM, and I wonder from your in-house tool of a digital twin, what are you extracting, and what's the ideal kind of parameters or ideal scenario you try to achieve with your digital twin?
So I'm not an expert on exactly, but I mean you can get loads of data, and we've been working quite closely with the FDA, mostly from the US side, showing you can basically set what you want to get off the machine in terms of the data that you want. What was the other part? What parameters are we?
You mentioned hold up mass.
Hold up mass, yeah.
Get hold up mass from
Yeah, the whole thing. So it's sat on load cells. So we've linked, we've linked this up to our historian, and essentially we can assign a tag to anything, and we can record that and look at that in real time, or play it back afterwards, and we can see the effect. So not when we're doing a clinical batch, but when we're doing development work, we can play around those parameters and we can see the effect kind of either live. Generally, we have when we're doing those experiments, we'll have a whole group of people in the room, and we'll be looking at all the parameters like hold up mass, feeder rates, speed, impeller speeds, and then the NIR as well. We'll be getting that live into the control room, and we'll be looking at the effects of that. So we can, and then we can, over the runs we've done, we can build up a model, which is more like a prediction of like what's a golden batch, what's the settings that we need to start with, essentially based on the API material that you're putting in and the excipients. Try not to change the excipients too much, but certainly based on the API. So yeah, you can pretty much, it's separate to, you need to set up your network, your historian. You need to think about what tags and how you do all that stuff. But you can get any amount of data you want out of it. Too much, to be honest.
Unless I'm allowed a question. Okay, I was just trying to get back on track. We'll take one more quick question and then we'll break.
Hi, Scott.
Hi.
You mentioned that some APIs that you've been looking at are not suitable for continuous. Would you like to expand on that and why you felt that?
It comes down to the kind of operating space. I think I was here yesterday, and it's a completely separate thing, but talking about solubility. Hence why we're looking at wet granulation. It's really around the characteristics that you're looking for. But if you can't get the right drug loading through a direct compression, you might have to look at wet granulation. You might have to look at, and at the moment there are some APIs that we have coming through that just don't very easily fit onto the continuous manufacturing model. We're trying to get a big chunk of those to, our ideal is to get 80% of our portfolio able to be done through continuous manufacturing. We're not quite there, but some of that is around, that we make certain assumptions about the portfolio, but there's all sorts of things that can happen. So products come from elsewhere, not Pfizer developed, so the API is already there. And it really comes down to the API properties and what the drug loading, etc., you're trying to get onto the tablet. So if you had a API that came in that was not very soluble, and you can get compressibility issues as well and things like that. So there's a kind of window. We've kind of, as I said, part of doing this, there's a kind of window, if you like, of API characteristics that we think fit really neatly onto it, and then there's a kind of boundary layer. And what a lot of the work we're trying to do is increase that. So some of those APIs that are kind of on the outliers, we can get onto PCMM. Wet gran is a kind of example of that. It's slightly different because you've got a whole different stream, if you like. But the principle is, instead of doing batch wet granulation, moving it onto continuous. That's because those APIs don't work through direct compression, or you can't get the right drug loading.
Great. Well, thank you, Scott. Really interesting presentation, so thank you.